To find the area of our, remember we said you should probably graph this thing. You have a calculator. Your graph should look something like this magnificent drawing I'm about to do for you.
I hope it's good. It's not, I'm gonna be mad.
Well, be mad, Joseph. It goes up like that. It comes down like that. That is the curve 20 over 1 plus x squared. And then we have the line y equals 2 way down here. Boom. Okay with this? We should be. Now, we want to find the area of this thing, so we need to find those points of intersection. You can use your calculator, but it should be easy to see that these happen at -3 and 3. Okay with that? To find the area of any region in the xy plane, you're going to integrate from left to right the top function minus the bottom function. So in this case, that will be the integral from -3 to 3, the top function, which they call, oh, they just called them y. Sometimes they call them, Joseph, f of x and g of x, and you can just write, this is what you're going to write in your paper, by the way, gang. You can just write f of x minus g of x, that's fine. Since they didn't call them that, you got to write out the functions. Are there any questions on what I'm doing right here? That's how you do the first one, that's A. You put that into a calculator, you get an answer. Anybody got an answer for me here?
37.962.
Everybody got that? Now listen, to get full credit for questions like this, you've got to put down the integral you did. I know you're using a calculator. Do not just put down the number your calculator tells you. Anytime you do a calculation on a calculator, like an integral or a derivative or something, you've got to write down what you actually did. Now, you don't have to type like fn int or anything like that. Just say the integral from whatever, -3 to 3 of this function equals this number, okay? Don't just put down the number. You will not get full credit.
So just write down the expression.
Yes. Okay? That's A. Hopefully that's easy. B, we want to rotate that thing about the x-axis. All right? So what that means is, I'm just going to go ahead and draw it again so we get a little bit more room down here. Cool. We have this thing here. Then we have the line y equals 2. And I want to rotate around the x-axis. Okay? So remember I told you to put a dotted line on the line you're rotating around? Looks like that. This always comes down to that same formula. It's pi, when you're doing a revolution, times the integral of big R squared minus little r squared. In this case, we're doing dx because we're going around a horizontal line. So we got to find big R, we got to find little r, but we know our integral is going to go from -3 to 3. The way we find big R and little r, remember we said, take your pencil, put it on the axis you're rotating around, draw it to the outside of your shape. Do it in a couple places and make sure you're hitting the same exact curve every single time. What's the top of every single one of those big R's? 20 over 1 plus x squared. And the bottom is?
2.
No, 0. The bottom of, because we're spinning around 0, not 2.
Oh,
Okay? So big R is 20 over 1 plus x squared minus 0. You don't have to write minus 0, but I like to do it so you see that you're doing top minus bottom always. Okay? It's not really doing anything there. There's a pi out here. We're integrating from -3 to 3. And then we get subtract off little r. Well, little r, if you erase all the big r's that I did, I'll just erase everything for some reason. Okie dokie, computer. There's 2, there's the axis. Boom. Little r is going to be to 2. You guys see that? You stop when you hit the curve for the first time, the shape for the first time. So little r is just going to be 2 minus 0. Are there any questions on that? Anybody got an answer for this? You got to be careful when you put your parentheses in. This 1 plus x squared, when you put it into a calculator, has to be in parentheses.
It's 595.61.
595.61?
No. Yeah,
Point. Okay, so what's the final answer? 0.190?
No, it's 10. Multiply that by 10.
Boom.
0.1.
Okay, I should look the answers up for you. Guys, let me say this too. We're going to do a bunch of these free response questions. Okay, hang on, David, I got you. We're going to do a bunch of these free response questions, gentlemen. The answers to these will always be online. The way you're going to find them, check this out. Go to your Google here, and you're going to say, okay, Google, Calculus AB 2007 free response answers.
False.
Boom. And they're right there, okay? There it is. Answers, okay? Isn't that nuts?
Okay, Google.
Okay.
It would have been nice.
So, for the OK Google trick to work, you have to be using Chrome and you have to be on the Google page. Although it did just make that little beep noise, so I don't know if it's recording me right now or what. I don't know. It's also sending everything I say to the Google headquarters, so they, have me on file of saying intelligent things to a bunch of teenagers. It's good. So, back to this. We're not going to talk about your incognito browsing, Danny. Who knows?
Because I want to buy a present for my parents, but I don't want them checking my history.
That's a good. What's wrong with you? Let's talk about C. Listen, A and B for this question, I'm hoping at this point makes sense. Unless you weren't here a couple days, that's fine. That makes sense that you don't understand. Okay? Tibet, I'm sorry you had a question. What was it? Scroll down a bit. Shh, let's all be quiet. Further.
Okay, so why do you send the function minus 0? Isn't that
It is. I'm just getting you guys used to writing like the top part minus the bottom part. That's all. It happens to be 0, so it doesn't matter. But if I like how we're all very quiet. If we were rotating around the line like -3, then it'd be the function minus -3. That's all. Cool. So no, you don't have to put the -0 there, technically. But okay. So let's talk about C real quick. We're going to do a little mini lesson on this. You ready? Let's check out this language here. There's 2 different types of volumes we find in the Calc 1 class. The first kind is the kind we ever looked at, the rotations. We're rotating around a line. It creates like a big donut-looking shape. Okay? But sometimes they say that the area we're looking at, in this case R, that's this area right here, sometimes they say that it's the base of a solid, meaning that's the actual bottom like footprint of a shape. Okay? And they're telling us that the solid has cross-sections that are perpendicular to the x-axis. That sounds super duper complicated. All right? Let's discuss what a cross-section is. A cross-section is what the inside of something would look like, what shape it would look like. So, for instance, if we take a cylinder like this one here, and if I chop this horizontally, like right there, chop, what shape will be on top? A circle. Like the two-dimensional shape that would be right on top is a circle. That's a circular cross-section. Make sense? If we were to chop it this way, chop, what shape would we be looking at? What? Okay, true. But I'm talking about in here. What would the cross-section be? It'd be a very ugly-looking rectangle I just drew there. All right, but it would be a rectangle. Does that make sense? If you chop a cylinder like that, the cross-sections, like the inside part of that, would be a rectangle. Okay? They're telling us that for this shape we're about to look at, this is the bottom, but the cross-sections are semicircles perpendicular to the x-axis. So what that means is, if I was to, let me draw that shape again. Here's what it looks like a little bit. Cool, kind of like a normal model, sort of, whatever, I don't know. Or a Pac-Man ghost, whatever. A fancy hat.
It's a T model.
This is the bottom of a shape that's, you can imagine it's sticking out of the board right now. It's sticking out of the screen. Okay? And if you were to chop it like this, hi-ya, like that, okay, you'd be looking at a semicircle. So this is going to look really ugly, but there's like a semicircle kind of thing like that sticking out of this thing. Everywhere you can see these are like semicircles sticking out of here. Okay? That looks really ugly. I'm going to show you a better example right now. Let's go ahead and take a look at my friend Mathematica. So, ready for this? This is an area in the plane. It's a square. You see the square right here? There's a square there. It's between the line y equals 1 and y equals -1. The cross sections that are sticking out of the board, I'm saying right now, do you see how I have semicircles highlighted there? Are semicircles. You know what that would look like? I'm going to show you. Oh, look at that. It'll look like that. Do you see that the bottom is that square and there's semicircles sticking out? So technically they're saying it should look like this. Cool? And there's semicircles sticking out of it. Actually, I guess they'd be perpendicular to the x-axis like this. But anyway, you with me here? It's a square looking like it, but it's sticking out of the board and there's semicircles like that. Cool? If they were equilateral triangles, it would still be a square on the bottom. You see the bottom is a square. Whoa, what just happened there? Okay, but the sides you can see are equilateral triangles. The point is this. The shapes are made up of the 3D shapes are made up of the same two-dimensional shapes repeated over and over and over and over again. All right? I think a better example actually is right here. This right here, they didn't put the axis, but you can imagine like the y-axis should be right down here, and the x-axis should be right here. These two parabolas are x squared minus 1, which is this one. This is x squared minus 1, opening upward. And this is 1 minus x squared, opening downward. The region we're interested in is the region that's between them. All right? Right now I have it highlighted that the region between them is made up of triangles sticking out of the board. You know what that looks like? Hey, it looks like that. See how it's all a bunch of triangles in there? Okay? Now, it's hard to draw that myself, but thank you, computer imaging. You can see that it looks like that. If I change the shape to semicircles, it's still the same base. It's still the same region between the two curves, but now sticking out of the board are semicircles. So it looks kind of like a snail kind of thing. If I made them squares, now do you see it's made up of a bunch of squares sticking out of the board there? But the squares are cross sections and it's a nice smooth shape. It's kind of weird. I've got a couple concrete examples to show you. I had some kids make some examples a few years ago. So hang on, let me pull whatever. Okay. So the question we had to answer was that's the base of a solid, and we have these squares sticking out of the board, really. Okay. Let me try to draw this the best that I can. Imagine I can actually pick this shape up and kind of turn it sideways a little bit so you can see it. So it might look something like this. Like, it doesn't look much better, okay? But imagine this is semi-3D, like on your 3DS you might play. Okay? What we're saying is there's like a square sticking up out of the board like that. Does that make sense? Okay. What? Oh, it's semicircles? That's a little harder to draw, but okay. Semicircles will be something like that, right? You guys agree that's sort of a semicircle sticking out of it? Okay. Over here, there'd be a smaller semicircle sticking out. Okay. What we want to do is find a formula for the area, well, really volume. These are like super thin slices of semicircles. We want to find the volume of them and add them all up. That's the integral. Okay. So the problem is the only thing we know is that this distance here, right there, remember this curve up here was 20 over 1 plus x squared, and this curve down here was 2. So the distance, no matter where I draw my semicircle, there's one here, I could draw one here. The distance of the entire semicircle, which is called the what of the circle? The diameter. The diameter is the top part minus the bottom part, which is 20 over 1 plus x squared minus 2. Does that make sense? For right now, I'm just going to call that just B for base of the shape. The base of the entire shape is B. And what we're going to do is come up with a formula for the area of a semicircle, multiply it by its thickness, that'll be the volume of one slice, and add them all up with an integral. So, the formula for a semicircle, I think we can all agree, should be 1/2 pi r squared, true? The problem is we don't want it in terms of radius, we want it in terms of that whole base, because that's what we see. We see the whole base, we see the footprint. All right? So we just said the entire base is really the diameter of the circle. So in terms of the base, the radius is just half of that. Everybody with me on this? If we take half the base, that's the radius. Squared times pi divided by 2. That's the area of semicircle. If I simplify this out, I get b squared over 4 here. There's a pi and there's a 1/2. And just to simplify this, and this is the formula you're going to memorize, okay? But I'm hoping you kind of understand where this is coming from a little bit. The area of a semicircle is pi over 8 times the base of it squared, which is the base is the diameter. I'm calling it base so that we have like a similar concept for all these different shapes we're going to do. All right? Then we need to multiply it by how thick that thing is. But remember, this is like x right here, right? This is our x number line here. How thin do I want this slice to be? I want it to be infinitely thin, and we're going to call it dx. Okay? So what we have right now is a area of it, of the face. To get the volume of the entire slice, we multiply it by dx, and then we have to integrate it from where the shape starts to where the shape stops, from left to right. And we said that it starts at -3 to 3. Whoa. And then all we got to do is put in, so guys, this right here, without the -3 to 3, is the formula for the volume of any shape that has semicircular cross sections. It's pi over 8, the base squared, integrate it. times dx. Okay? We're going from -3 to 3 because that's where our shape starts, and we got to put in what the base is. But since the base is the length from the top curve to the bottom curve, we're going to do 20 over 1 plus x squared minus 2. So to answer C, it's pi over 8 times the integral from -3 to 3 of 20 over 1 plus x squared minus 2 squared dx. How do we feel about that? You feel good? I feel good. Does C ask us to actually find the answer? Does it say write? Oh, it says find the volume. Sometimes the question will say write but do not evaluate the integral that will find the volume. So they just want to see what the integral is. But in this case, they want you to actually put that into a calculator. All right? So this is all you're going to put in there, and it's going to be a number. I have the answer somewhere. Boom. So try it out, but you should be getting 174.268.